Swayam Prabha. Digital India. Educated India.
Hello, good morning students. Welcome to today's class on a comprehensive view of speech processing, and today's lecture is lecture 30 in the series, and today we are going to discuss about the statistical pattern recognition and part of the probability density estimation. So far in last two lectures we are discussing about the various concepts related to the statistical pattern recognition, and today we are trying to complete the basic terminology or basic the concepts related to the statistical pattern recognition. Next we move on to the later topic, that is a probability density estimation, which is an extension to the like the concepts of pattern recognition that we will see. So in this we have covered the contents, like here you can see start from the pattern classification, pre-processing, cursor dimensionality and so on. So yesterday we are going to discuss about the Bayes theorem, right, and today we will begin with the Bayes theorem, and then we will discuss the other topics related to that, like using a Bayes theorem. How does the Bayes theorem or Bayes rule is used for a classification problem for automatically classifying the feature vectors into one of the classes. So and then afterwards how the decision will be done, what will be the inference using a Bayes rule in the case of classification problem, and what are the decision boundaries, and finally for carrying out the classification using a Bayes rule, and we need to estimate the posterior probability is nothing but a probability of a class given the feature vectors. So for estimating the posterior probability, so we need to carry out the estimation of the probability density function of the feature vectors of a given class. So that way, what are various techniques to estimate the probability density functions, and those things we will discuss later in detail in the later classes also. Yeah. So yesterday we have discussed this by considering a simple example of two class problem, as we discussed from the beginning of this the discussion on statistical pattern recognition. Consider the two class problem, and here we have taken a numerical example by taking the 100 examples. Out of that, the 70 belongs to class 1 and the 30 belongs to class 2. And from each of the example, because as we know that here this is a handwritten character recognition problem, and where the problem is simplified to only two characters A or B, and so we have taken 100 examples. Out of that, the 70 belongs to class 1 and 30 belongs to class 2, and from each example is nothing but here the character A or character B is given in the form of an image of 256 cross 256 pixels resolution, and from that image we extract the feature, right. So here the feature is that height by width ratio of the given character. So that way, from each image we extract a feature which is a single value, height by width ratio, and we compute one value for each image. So likewise, for 100 examples we have each image gives you one value. So there are about 100 features, right, corresponds to 100 examples, and those feature values you can see it's in the x axis, you can say here, and that will be discretized into 8 bins, right, based on the range from lower limit to the higher limit. It was divided into 8 bins, and then based on the value we place those feature values into appropriate bins. So you can see there are 70 values are distributed in class 1 and 30 values are distributed in class 2, right, and these are the bins. There are 8 bins, offers a range from lower limit to its higher limit based on the values whatever we got, right. And then here, based on the probability theory, we know that a joint probability between the two variables, like here the class label, and the other one is the feature vector. The joint probability of a feature vector and given a class label can be written in terms of its conditional probabilities and prior probabilities. So, this is from this definition can be derived, can be there in the very basic probability class. You can come across that. A joint probability can be written in terms of a conditional probability and a prior probabilities. So, that way this probability of Ck comma x, joint probability of Ck x can be written as this way, these two ways, but taking one of them and conditioned with respect to other, like probability of Ck given x into probability of x, otherwise probability of x given Ck into probability of Ck. So, these two are equivalent, and these two are equal to this particular joint probability. And now, by taking a numerical example with the numericals, with the number of examples falls into different bins, into classes and all. So, we have discussed this one yesterday, and we have seen that if you directly look at the joint probability and the same thing that is estimated from the conditional probabilities also, we got both of them are same. Then we also explained about, after knowing about this probability, basic probability concepts. So, here you can say that we can write this joint probability of Ck comma x can be written as in terms of conditional probabilities, and then here by rearranging the terms of these two equivalent expressions, probability of Ck given x into probability of x equals to probability of x given Ck into probability of Ck, right. So, from these two terms here, if you can rearrange that, suppose you probability of Ck given xl can be written as, here xl means since it is a discrete one with respect to a particular bin, feature vector corresponds to a particular bin, otherwise it is simply x is a continuous in a continuous space. So, probability of Ck given x can be written as from these two expressions. So, probability of xl given Ck into probability of Ck by probability of xl. And here the terms that are here over here in this equation, probability of Ck given x can be known as posterior probability. That means, here the probability of a class, specific class, by observing the feature vector. That means, given a feature vector, estimating the probability of a class label, estimating the probability of a class label, right, probability of class label. It is known to be posterior probability, because after you observe the feature vector, you are trying to estimate the probability of a class, posterior probability. And likewise the other ones, this is known to be probability of x is nothing but probability density function of a feature vectors, and here condition to a class. So, therefore, it is known to be probability density function with respect to a specific class. It means that, for example, if you take the examples of A or images of A, from all of them if you extract the height by width ratio, and then if you try to estimate, or if you try to find out the distribution of that, it is nothing but the probability distribution of the feature vectors belongs to the character A or a specific class A. Likewise, so that way this probability of xl given Ck is known to be class conditional probability. That means, probability of feature vectors conditioned to specific class, known to be class conditional probability, right. And the probability of Ck is known to be prior probability. It means that here there is no condition is important, just simply some if you ask that what is the probability of occurrence of A. So, if you know that, or if you have some domain knowledge, if you have some knowledge about that history of that, and based on that, if you can able to tell something about probability of the like a class of a given class, without any observation, without looking at the feature vector, it is known to be prior probability. Like, for example, you see that in the case of summer, for example, right, in case of summer, we know that it is mostly sunny, the probability of rain will be very, very less. So, that way you can say that since we know that it is a summer, peak summer, so the chances of rain will be very less. So, you can say that the probability of sunny will be almost like 0.95 or 0.98, something like that, right, since we know that it is a sunny, right. Suppose, for example, if it is a rainy season, for example, then you can say that the probability of a rain will be like it is about like a 0.5 or like a 0.6, 0.7, something like that, because we know that we experienced that, we aware of that, yeah, this season is a rainy season. So, therefore, the chances of rain, the probability of rain will be something like some 60%, 70%, something like that. So that is known to be the prior probability. So that means without knowing without observing the parameters or feature vectors, estimating the probability or commenting about probability known to be the prior probability. Likewise, for example, in the case of English literature, English words vocabulary, for example, where like a particular occurrence of a particular character, for example, you say that suppose among the characters you can say the probability of occurrence of a particular character. That means if you observe the English script and a lot of English script, and from that if you can able to estimate the occurrence of each of the character, and from that if you can able to comment on the, suppose for example we know that in English probability of occurrence of alphabet Q will be less compared to remaining alphabets, right. So that way, so this is known to be the prior probability. That means by knowing the statistics, right, commenting about the probability of a particular thing known to be prior probability, right. And that is, for that we need to know about the domain knowledge. We should have some knowledge about the particular the quantity, then only we can able to comment on it. And P of XL is nothing but simply it's a unconditional probability. That means again there is no condition imposed on that. What is the probability of feature vector, right? What is the probability of feature vector? It's going to be simply unconditional probability. And as you see that in this particular equation, the probability of XL will be there as part of a denominator in this expression, right. So here probability of CK given XL, where CK is nothing but class label. So that depending upon the problem, we have several number of classes used to be there. In the given example, we have only 2 classes. So the CK happens to be either C1 or C2, right. So in both the cases here, you can see you have the same denominator used to be there. And the same way, suppose we take a generic handwritten character recognition, we have 26 alphabets. So it means that the CK takes the values of like 26 total, C1, C2, C26, right. Each corresponds to one of the character, right. So for all these 26 classes, 26 posterior probabilities, you can see that the denominator remains same. The denominator remains same, whereas the numerator it varies depending upon the class label. The numerator varies, but denominator remains same because this is unconditional, right. Probability of X, whatever it may be, whatever the class it may be. So therefore here when you are estimating the posterior probability, the role of denominator or the role of this probability of XL remains same across all the classes. So therefore its effect will not be there in estimating the posterior probability. So therefore this not be normalization factor also. So therefore when you are trying to estimate the posterior probability, you need not bother about the probability of XL because this remains same. This is a common division for all the posterior probabilities. So therefore there is no point, we need not bother about really how to estimate this or what is its impact on the posterior probability. That we need not bother at all because that remains same for across all the posterior probabilities, right. So and as we have already mentioned that we can able to, for example, given a classification problem and for a given feature vector, here the objective is that given a feature vector, we need to estimate that, we need to predict that this feature vector belongs to which of the classes, or this feature vector belongs to which of the character, either A or B or C or whatever. And all. So for that what we are doing here, we are trying to estimate this posterior probability and like for each class for the given feature vector, and then we will try to see that whichever the class has giving the highest posterior probability among the given classes, so that class label will be hypothesized to that particular feature vector. That means given a feature vector, we will try to estimate the posterior probability for all the classes, and among these posterior probabilities whichever is the highest, and that particular class label will be assigned to that particular feature vector, right. So here this result is known to be the Bayes rule. You can see the posterior probability equals to this one, class conditional probability multiplied by the prior probability and divided by the unconditional probability. So as I mentioned, this unconditional probability has no role, has no impact on the estimation of the posterior probability. So we can write that, we can say that the posterior probability can be estimated directly using a numerator itself. That means probability of XL given Ck into probability of Ck. It means that for estimation of posterior probability, we have to estimate this one, the class conditional probability, and the prior probability. Both of them we need to estimate it. And the prior probability, for estimation of prior probability, what we will do? Based on the knowledge, based on the available statistics, or based on the history that is known, based on that the probability of Ck can be estimated. Suppose we do not have any knowledge about the problem, simply we have a data is available, and from the data if you want to find out the probability of we need to find out the posterior probability. At that time, since we have no knowledge about the given data, so therefore we will assume that these prior probabilities are equiprobable. It means that the prior probability is nothing but the probabilities of a class, the probability of a given class, right. So since we have no knowledge about that one, so we can assume that all the classes are equiprobable. So if all the classes are equiprobable, it means suppose if we have 10 classes, then for each class the probability will be 1 by 10. So therefore that means the probability of Ck remains same across all the classes. So therefore in that case, even the impact of the probability of Ck or effect of probability of Ck is also not much. Not much means it is not at all affected. So in that case, we can say that the posterior probability completely depends on the class conditional density. And usually this class conditional density or the probability density with respect to a specific class, this will be estimated by using different approaches that we will discuss later on. One of the approaches will be using parametric approaches. It means that we will assume a particular functional form, and by observing the data, right, we will try to optimize the function, or we will try to maximize the function, so that the probability density estimation will be better or more accurate and all. So since we are assuming this in the functional form, and for accurate estimation of probability density, we are trying to maximize this function, right, by optimizing the parameters. So therefore this is also known to be maximum likelihood. This is also known to be maximum likelihood function. So here the terminology here will be, this is known to be class conditional density, or this is also known to be the maximum likelihood or likelihood function and all. So this particular functional form, whatever we have chosen, that we will try to optimize, that we will try to maximize that, so that the estimation of probability density will be more and more accurate. Here related to this, we discussed yesterday, these are known to be like posterior probabilities, like posterior probability related to class 1 and class 2, and as we know that based on the feature vectors for the class A, the feature vectors are, you can say that the feature vector x1 will be lower values, and whereas for class 2 it will have higher values, and whereas in between there is certain range where both the class 1 and class 2 features will be overlapped, and where this leads to a probability of error and all. Like there are chances of misclassification takes place if a feature vectors, if the feature values falls in between this range, and whereas below this range or above this range we do not have any misclassification at all. We will get the accuracy will be 100%, whereas if the feature vectors like value will be within this range, then there are chances of error, right. And yeah, this we have discussed, this is known to be posterior probability, and we know that since it is a probability with respect to each of the class, suppose if you take in a feature vector and the feature vector may belongs to one of the classes. So each class may have certain probability of claiming that a feature vector belongs to that particular class. So therefore if you sum up all these posterior probabilities with respect to the classes, number of classes, then it should be 1, that is a rule, right, because the feature vector should be in one of the classes. So each class will claim some probability with respect to that particular feature vector. So therefore if you sum up all those posterior features, that remains 1, it equals to 1, right. So that way this is nothing but posterior probability. Then if you substitute this with respect to the base result on the right hand side, right. So this is nothing but a class conditional density and prior probability and unconditional probability. So this is equals to 1, and so therefore and then by rearranging that, here the denominator can be brought this side. So that way we can able to estimate the unconditional probability, that means probability of a feature vector XL can be estimated based on this. It means that It's nothing but this one, the way we for estimation of posterior probability, whatever the numerator that is considered, if you sum up all of them, then that gives you the probability of XL, right? Because the probability of XL, that may be belongs to either class 1 or class 2 or class 3. So therefore, if you want to estimate the probability of XL in an unconditional way, then it can be estimated by summing up all these terms, summing up all these expressions, like with respect to different k values, that means with the C1, C2, C3 and so on. So in case of a 2 class problem, we know that k equals to 2, there are only 2 classes. So therefore, we know that these are the posterior probabilities and this is sum equals to 1. So the probability of XL in case of a 2 class problem is nothing but this one, probability of XL given C1 into probability of C1 plus probability of XL given C2 into probability of C2. So that way we can able to estimate the unconditional probability or probability of a feature vector without condition to any class. Yeah. Then coming to the how do you make a decision? How do you make a decision? We know that we already seen that using the posterior probability we can able to make a decision. Given a feature vector, we will try to estimate the posterior probability of that particular feature vector with respect to each of the class. Then we will try to estimate that whichever the class gives the highest posterior probability, then we will hypothesize that the given feature vector belongs to a class which has the highest posterior probability. So the same thing here we are mentioning here. We already discussed about this result. This is known to be Bayes result and it's a posterior probability, and this is the way it is estimated will be based on this. And the decision rule will be like, so we need to make a decision such a way that the probability of error or probability of misclassification should be minimum. Probability of misclassification should be minimum. So that we can able to do it by using a Bayes rule, by assigning the class label to a maximum posterior probability, by assigning a class label to maximum posterior probability. So in form of like using this in the mathematically, you can say that the label Ck will be given, the label Ck will be given, that means the label of a class will be estimated based on this one. We will estimate the posterior probabilities and we will see that the probability of Ck given x greater than probability of Cj given x for all j not equals to k. J not equals to k. That means if you estimate all the posterior probabilities and we need to pick up a posterior probability which is highest. So with this expression, if you do that, then you can get the appropriate posterior probability whichever is the highest among the classes, and that label will be given, that label that k is given, that Ck will be given. So the posterior probability, as I already mentioned, that is a class conditional density, and since the class conditional density is estimated by using a functional form, so therefore we will try to maximize that function, right, outcome. So therefore known to be likelihood function, or they are known to be maximum likelihood and a likelihood function and a prior probability by the normalization factor. The next one is that here, what are the decision boundaries? That means how do you make a decision such that the probability of error will be minimized. So here if you look at here, these are the class conditional density. That means from the previous example what we have seen, we have taken the 2 classes and certain number of examples from each of the class, and we computed the feature vector, and if you compute a distribution, if you see that this is the distribution of probability of x given C1 and this is the x given C2, and assuming that this is the region R1 and this is the region R2, and our hypothesis is that if the vector falls in a region R1, it means that it is a class C1. If the vector falls into region R2, then it becomes C2, and in principle these regions R1 and R2 should be non-overlapped. If they are overlapping, then it results to be erroneous, right. So therefore here we can write the probability of error as, probability of error can be written as, in case of 2 class problem, probability of error can be written as probability of x belongs to R2 but its actual true class will be C1. The probability of the given feature vector, its actual true class is C1, but if it falls into R2, then that results to be erroneous, because when it falls into R2, then we will decide that feature vector as class 2, belongs to class 2, but its actual class is C1, then it results to be error. Likewise, the other way also, the probability of feature vector that falls into R1, but its true class, actual class is C2, then only we have error, where we are ending up with error, because when it falls into R1, we will hypothesize that as a C1, but its actual true class is C2, therefore we end up with error. So therefore the probability of error can be estimated based on this one, like a probability of feature vectors falls into R2, but its true class is C1, and the other way, the joint probability of these two, if you sum up, then we can get the probability of error, and that we have to minimize that. We try to minimize that various ways, either increasing the feature vectors or like by using appropriate decision mechanism and so on. So this since it is a joint probability, you can able to write like this. Joint probability can be written in terms of conditional probabilities, right? Probability of x belongs to R2 given C1 into probability of C1, likewise you can write. And this is nothing but probability of x given C1, right, which is belongs to R2. It means that we can able to write this as like the integration over probability of x given C1, right, into probability of C1 dx, and the same way the other way also, like a probability of x given C2, right, which is falls into R1 into probability of C2. So that way we can able to compute the probability of error and all, right. So this way you can able to compute the probability of error. And the other way, suppose you want to analyze the probability of correctness, right, the probability of correctness is nothing but probability of the feature vector falls into a region Rk whose label is also Ck, then there is no issue at all, because the class label is Ck and it is also falling in the region Rk, which is the genuine one. So therefore there is no error at all. So likewise, if you want to estimate the probability of correctness, then we need to perform the summation over all the classes of this particular expression, then we can able to get the probability of correctness. So it means that what we need to do is that when you are taking a decision boundaries, or when you are formulating the things, where either we need to see that the probability of error has to be minimized or the probability of correctness has to be maximized. One of them has to be carried out. If we do one thing, then automatically other things will be taken care. So with this we more or less covered the basic aspects, or you can say the introductory terminology that is required for the later part, like building the speech models, right, for carrying out various speech tasks. So this is somewhat introductory that is required, the basic stuff, what is classification, what is a feature vector, what is meant by pre-processing, right, how do you approximate the function in a very simple way using a polynomial curve fitting, and in that what are the various issues will be there, right. And suppose if you, because since we know about the underlying function, if you try to estimate with a very simple model or with a very complex model, then what are the consequences, then how do you estimate the accurate complexity of the model and all. So for that we introduce the terms like generalization, regularization and so on. And finally, for carrying out the classification task, to perform a classification task, so one of the approaches will be using a Bayes result or Bayes theorem. We can able to perform a classification by estimating the posterior probability, right. So as we have seen that for estimating the posterior probability, right, the posterior probability can be estimated of a class, can be done by using estimating the class conditional density and the prior probability. And since if we, suppose for example, if you do not have any knowledge about the data or a problem, given problem, then even the prior probability also will not come into the rescue, because we do not know about the nature of a classes of a given problem. So therefore we cannot assume anything, because we do not have any history, we do not have any knowledge about the given problem. So therefore we assume that like all classes are equiprobable. So in that case the prior probability also will not affect, or will not affect to the will not give any effect on the posterior probability. So therefore in that case the posterior probability completely depends on the class conditional density, right. So we will see that, that means the class, how do you estimate the class conditional density. So that is about the next topic, and today and then even the next class also will come, will going to discuss about this particular topic. So, it is known to be like a probability density estimation in a very generic sense. It is nothing but, suppose if you estimate the probability density of a feature vectors confined to a particular class, it is known to be class conditional density. So, the generic way is that, suppose if we have a data belongs to different classes, and then we will try to estimate the probability density for each class separately, and then we will try to estimate the, for a given new feature vector in case of testing process or evaluation stage, we will get a, for the given data, for the given test data, we will try to extract the feature vector, and we will try to estimate the posterior probability of this particular feature vector with respect to all these the given class densities and all. So, whichever gives you the highest the value, then that particular class label will be hypothesized for the given feature vector, right. So, in that case we need to, first of all we need to like come to know about the posterior probability, but the posterior probability is indirectly evaluated by the class conditional density. So, that way the probability density estimation is very much required. So, we will see that what are the various techniques or methods to estimate the probability density function, right. So, here from this you can see here there are various methods, like at a gross level we can assume that there are 3 different ways you can able to estimate the probability density, right. So, the first one is the parametric methods and the non-parametric methods, which are completely like orthogonal, right. You can see it is a parametric, non-parametric, we will see that what they are and all. And the third one is that it is a semi-parametric, like it is a via media, or like it takes the like maybe the advantages of both of them, right. So, in case of parametric methods, so the way we estimate the probability density of a given data will be carried out by using these two methods, one of these two methods, right, either maximum likelihood estimation method and or the Bayesian inference method. We will see that what these techniques are. How do you estimate the probability density using these methods? We will see that, and both of them come under the parametric methods. And then coming to the non-parametric methods, right. So, these are the various techniques like histogram. It is a very simplified technique, but generally it is not used, just for illustration purpose. We can view the histogram techniques as non-parametric techniques, which we already come across, right. And the other two methods, these are the two methods that are in general that are used for estimation of probability density using non-parametric methods. One is the kernel based method, other one is the k nearest neighbor. And the next one is the Kullback-Leibler distance, that is known to be KL distance, and this is objective measure or distortion measure, and using this measure we can able to compare the two probability densities. Suppose for example, we know the data, the true density of a given data is available or known for us, and by using some techniques, either parametric or non-parametric techniques, we will try to estimate the density. And then the estimated density, if you want to check that how far the estimated density is close to the true density, right, or compare the two probability densities, or for example, you have a data, and for that data the probability density is estimated by using two different methods, and if you want to compare those two, for example, then we need to have some distortion measure or the distance measure is required. So, here in this case the KL distance measure is used to compare two probability density functions. And a semi-parametric methods is nothing but, as I mentioned that, so it takes the merits and advantages of both of these two, right. So, this under semi-parametric methods we discuss about the mixture models by taking the example of Gaussian mixture models. We will see that what it is and all. And here in this case, these methods, the semi-parametric methods can be carried out using these techniques, maximum likelihood estimation or the EM algorithm, that means estimation maximization algorithm. We will see the details of that bit later. Yeah, in the case of parametric methods means in the case of parametric methods, the way the probability density function of a given data will be estimated in the following way. Here in case of parametric methods, it means that we use some parameters with which you can able to estimate the density, and here the parametric method, what we do is that we assume or we just consider some functional form, some function, and then we will try to estimate the parameters of a function in a very optimal way based on the given data. So, it means that some specific functional form is chosen, and then by observing the data we will try to maximize that function. It is nothing but we adjust the parameters so that the function will be maximized for the given data and all. So, that way here, for example, we will see that, for example, if you take a Gaussian function, for example, right, Gaussian distribution function, for example, then the parameters will be the mean and variance. We know that how the Gaussian function look like, and the entire Gaussian function can be parameterized using the two parameters, like one is the mean and other one is the variance, the spread around the mean, right. So, those are the two parameters, right. So, likewise for a different functions we have different parameters used to be there, and here in this case the parametric methods, what we do is that first we will assume some functional form and we will try to fit the data into that function, and we will try to estimate the parameters, right, from the given data with respect to that particular function, and those parameters like defines the distribution or the probability density function. So, therefore, in case of parametric methods the specific functional form is chosen, right, and for that the evaluation is also very faster. The evaluation for a new data is very fast in case of parametric methods, because we know that a data point is added and already we have certain parameters, then we can easily compute the new parameters of a function, right. And here the problem with these parametric approaches will be, we choose the function a priori without looking at the data, and we do not know, we are not sure that the data fits into the function like accurately or in every optimal way or not, because the data, the nature of the data or the shape of the density function of the actual data may be very different from the functional form what we have chosen. We are assuming that the functional form is Gaussian, but the data that is available may be uniform distribution, for example. In that case we are trying to force the Gaussian distribution on that, where the density estimation is not accurate at all. So, that is the problem with the parametric approaches, but the advantage will be like it is faster, you can able to estimate the density at very fast for the new data. Whereas, in case of non-parametric methods it is completely the other way, orthogonal. We do not assume any functional form at all, and here we will try to estimate the density at every data point, right. At every data point we will try to estimate the density, and then we will try to like we perform the addition of all these densities put together, like that becomes the overall density of the given data and all, like. So, therefore, what happens here, the number of parameters grows with the number of data points, because at each data point we will try to estimate the density. At each data point centered around the data point we will try to estimate the density, and the same way we will try to estimate the density at every data point, right. So, therefore, the number of parameters will grows like proportion to the data, and in that case, that way, suppose if you want to add some new data, in that case the evaluation of the probability density will be very slow, because when you add a new data, then again we have to compute the density for all the points again. So, therefore, it takes lot of time to estimate the density in case of non-parametric approaches, but using a non-parametric approach the density estimation will be more accurate compared to the parametric approach, obvious, because the parametric approach a priori without knowing the nature of data we consider some functional form and we will try to estimate the parameters of a function that best suits to the data, but the data may not be of the form of the considered functional form, right. In that case we have whatever you do, the estimated parameters may not be optimal at all, or it is not truly represents the shape of the density of the given data. Whereas, in case of parametric methods, since we are not assuming any functional form and we are trying to estimate the density at every data point, and then we are taking the linear sum across all of them, linear addition. So, therefore, the density whatever we estimated is the true density, close to true density. And in case of semi-parametric approaches, the way we do here is that we will take, as I mentioned, the advantages of both. That means, here we do not assume any specific functional form, but at the same time we try to consider some functions in a multiple components, so that the number of parameters grows with the complexity. That means, if the data has a really complex data, then the number of parameters that are used for representing the density will be increases, so that it accurately determines. Suppose if the data is not complex, if the underlying data is not a complex one, so in that case we can use very few parameters to estimate the data, to estimate the density of a function. But here it is again, this is also computationally intensive, because since we do not have any knowledge about the given data, so therefore we need to try about using hit and trial or trial and error method, but with the different possibilities and all. First we will start with the low complexity, and then afterwards we have to increase the complexity. Every time we have to check with the error that is underlying or error that is cropping up. So whichever model or whichever the choice gives you the less error, so we can finalize or we can converge to that the model, and that way it is slightly computationally intensive, right. So we will discuss about each of these methods one after another. So first we will start with the parametric methods. So here when you are considering the parametric methods, so here we will take an example of a Gaussian distribution, also known to be normal distribution. So all of us are aware of that, how the Gaussian distribution looks like, right. The Gaussian distribution looks like, you can see that it is a kind of all of us are aware of that. So here I am not specifically mentioned about that, or otherwise you can see that the Gaussian distribution will be kind of, you can see, you can see the Gaussian distribution will be, yeah, this is the way the Gaussian distribution looks like, right. So it means that actually here you have, this is the mean here, around this is the mean here, and this is the spread over that. So this is a simple Gaussian function of one dimensional case, right. So here if you look at here in case of here for a normal distribution for a single variable, right, for a single variable, the probability density function or probability density can be estimated from a Gaussian distribution with the given parameters. By using this expression, you can able to compute the probability density, or you can say the probability of a feature vector from the given Gaussian distribution or given probability density function defined by the Gaussian parameters, right. So P of x is nothing but probability of x is a feature vector, can be estimated from the Gaussian distribution. Here the Gaussian distribution, the parameters are the mu and sigma, where mu is the mean vector, and here you can say that this is the mean vector, like you can say in this case so this becomes the mean vector, right, and this will be the spread, right. So here you can say that this is the mean, like the center of the this one, and this is the spread over that. So you can say that the sigma square is known to be variance, where sigma is known to be the standard deviation. This we come across, like most of you are aware of it, where the sigma square is known to be variance and mu is the mean of the Gaussian distribution. So for a single variable, the normal distribution can be defined using this expression. That means by knowing the parameters mu and sigma, if you want to find out the probability of a feature vector from this particular distribution can be estimated by using this. That means by giving the feature vector, just by substituting the feature vector over here, and by knowing the parameters mu and sigma, we can able to estimate what is the probability of these feature vectors drawn from the distribution or the PDF function. Here I am using the terms like a distribution and the density function, because the distribution means it usually in terms of like a discrete case. Suppose if the data vectors are, if the like feature vectors are discrete, then we can say it is a distribution. Whereas if the feature vectors are continuous, then you can say it is a density function and all. That is the only difference, otherwise both remain same. So the mu can be estimated using expectation. This we all of us will aware of it, like given a probability density function, and if you want to find out E of x, expectation is nothing but x px integration over the limits. And similarly the sigma square can be estimated using the squared with respect to the centered around mean, like x minus mu whole square expectation is nothing. This is the way you can able to compute the parameters for a single variable. And now, but the problems, the practical problems what we mostly come across will be like the multidimensional case. So in case of multidimensional data, if you want to discuss the normal distribution for a multi-dimensional case, it is known to be a multivariate normal distribution. In case of multivariate normal distribution, the probability density or the probability of a feature vector can be estimated as P of x equals to 1 by 2 pi whole power d by 2, and you can say the sigma whole power half. This is here, this is known to be like a covariance matrix, because it is a multidimensional data, right. In case of earlier, we have only one variable, so therefore we say the sigma is the spread. Here also it represents the spread only, and here this is known to be like, since it is multidimensional data, d-dimensional data, where the sigma is known to be covariance matrix, and the size of this covariance matrix will be d cross d. That means there are d rows and d columns, where d is the dimensionality of a feature vectors, or you can say that the number of components in a feature vector. It is a d means number of components in a feature vector are known to be dimensionality of a feature vector. So, this covariance matrix of size d cross d, and since the dimensionality of a feature vector is d, so therefore the mean vector is also of size d, mean vector of size d, and this is the expression that this is just similar to the one what we discussed in case of single variable, and the only difference is that here is a d dimensional the features, like mu is the d dimensional feature vector, and your sigma will be like it is a covariance matrix. Earlier it is only one vector, only one value or a single scalar. So therefore it is like the covariance is nothing but just simply spread is having only one value. But here, since it is a multidimensional data, so therefore the covariance contains, the variance contains, like with respect to each of the component we need to evaluate that. So therefore it becomes a d by d, d cross d, right, matrix and all. So therefore if you try to analyze the independent variables or parameters mu comma sigma, where mu is the mean vector and sigma is nothing but covariance matrix. And we see that in the case of covariance matrix, if you look at the covariance matrix is nothing but, since you have a feature vector has d components, or you can say the d dimensional d components, the covariance is nothing but it tries to give you that what is the correlation between the different components. We have d components, like what is the difference between the first component to second component, first to the third, first to the fourth, likewise the second to the first, second to the third, and so on. So when you try to estimate all of them, that becomes a matrix, right. So each value in a matrix gives you the what is the correlation, what is the relation, or what is the dependency between these two components and all. So when you try to estimate that in the case of d cross d matrix, so the d cross d matrix appears to be symmetric. So it means that when you try to estimate a correlation between the component 1 and 2 and component 2 and 1, they remain same, both are same, because the relation or the correlation between 1 and 2, components 1 and 2 is nothing but components 2 and 1, both are same. So therefore when you try to analyze the covariance matrix, it appears to be symmetric matrix with respect to the principal diagonal, because so if you look at the first row, the values will be like 1 1 1 2 1 3 1 4 and so on. If you look at the column, it becomes, right, what it becomes 1 1 2 1 3 1 and so on. So therefore whatever the first row is there and the first column, so their values will be remain same. So that way in case of this covariance matrix, it is symmetric matrix. So it means that the values that are there in the upper diagonal and lower diagonal, they remain same. So therefore the number of parameters will be like, it boils down to d into d plus 1 by 2, because you have principal diagonal, right. If you look at the very first row, we have only one element will be there. Then if you consider the second row, we have two elements, third row we have three elements. So likewise if you come to the last row, we have all d elements used to be there. So therefore the sum will be d into d plus 1 by 2, and where d is again, another d is nothing but related to the mean vector. For mean vector we have d components, and for in case of covariance matrix we have actually d cross d values, but since it is a symmetric matrix, so the values that are upper diagonal and lower diagonal, above the diagonal and below the diagonal, they remain same. So therefore we can ignore either upper diagonal or lower diagonal, so that the number of values becomes d into d plus 1 by 2, and this is nothing but d into d plus 3 by 2. So that depends upon, suppose if d equals to 10, then the number of parameters will be 10 into 13 by 2, it is nothing but 13 into 5, so 65 parameters that will be used to represent a 10-dimensional data using a normal distribution, right. Suppose if it is a one dimension, we have only two values, mean and the variance, the mean and the variance spread. Both are scalars, so have only two values. So likewise, as you increase the dimensionality, then the number of parameters also will be increased. And here how do we, and here when you look at here, if you look at the example here, in case of two dimensional data, as we have seen earlier, in case of one dimensional data, how the Gaussian looks like, because it's like we have only one values, like if you take the feature vectors of x, for example x value, so this simply the Gaussian looks like the way what we have seen, and there the mean vector is nothing but we have one value and a spread is nothing but one value. And suppose for example, if I have two dimensional data, for example, if you plot a two dimensional data, then if you try to visualize the Gaussian distribution in case of two dimensional data, it appears like a bell, right? Here the depending upon the concentration of data points, here the height varies, here the height varies. Earlier we have a simple histogram, like with that actually you can see that in the given range whatever the number of points, that will be represents the height. So that way you can able to approximate the Gaussian distribution with a normal histogram also, right? What we have seen here, this is the two dimensional case. We have two dimensional case where here, that means here the space that need to be analyzed will be the plane. So therefore here when you try to estimate the density or distribution, the distribution appears like, in case of Gaussian, the distribution appears like a bell. We have a bell structure and all, right? And here the center of the bell can be viewed as the mean vector, right? And the spread is nothing but, here since it is a two dimension, the spread can be estimated in two different directions. So therefore here this way you can able to estimate the spread or the Gaussian can be approximated or can be illustrated like this in a two dimensional space. Suppose x1 and x2, these two becomes a feature vector, components of a feature vector, right? For that, if you estimate the density Gaussian distribution, so this becomes a mu, the mean vector, right? This becomes a mean vector, right? And so this becomes the spread, like the Gaussian bell is something like this, and here this Gaussian bell, the spread in the Gaussian bell can be analyzed using this one, the Mahalanobis distance and all, and that is nothing but, so here the spread in the bell, the Gaussian, or in case of multidimensional case, can be defined or can be indicated by the eigenvectors and all, can be indicated by eigenvector. That means whatever the data we have, so from that if you compute the eigenvectors, the eigenvectors indicate the direction of the maximum variance and all, the direction of the maximum variance. The eigenvectors indicate the direction of the maximum variance. So here since it is a two dimensional case, we have the two eigenvectors, one is the u1 and other one is the u2, right? So this is the direction, these directions indicate the maximum variance in the given data. There are two directions, this is the one and this is the other way. And the spread, the variance, the amount of variance will be indicated by the eigenvalues. The amount of variance will be indicated by eigenvalues, lambdas and all. And here these are related by the covariance matrix multiplied by eigenvectors equals to the eigenvalues multiplied by the eigenvectors and all. So that way in case of two dimensional case or a multidimensional case, the eigenvectors indicate the direction of variance, right, maximum variance, and the eigenvalues indicate the amount of variance and all, the amount of variance. And if you want to simplify the parameters further, because we have number of parameters equals to d into d plus 3 by 2, and if you want to simplify the parameters further, and if you assume that if the components are not related, if the components are independent, because if in the case of d-dimensional data, the dimensions or the individual components are independent, they are not at all depend each other, like x1 and x2 they don't depend upon. So in that case, if they don't depend, then the correlation between these two will be 0, right? So therefore our the symmetric matrix, the all values will remain 0 except the diagonals, all values remains zeros. So therefore here the symmetric matrix or the covariance matrix becomes a diagonal matrix and all, becomes a diagonal matrix. So in case of diagonal matrix, we have values only in the diagonal elements, and the remaining elements will be it will be 0. So therefore in this simplification process, the number of parameters will be reduced to 2d. How? The d will be the number of parameters related to the covariance matrix related to the diagonal elements, and another d will be your the mean vector, which is a d-dimensional vector. So it has a d components. So related to the mean we have a d components, and related to the covariance we have another d. So 2d will be there. And if you want to further minimize, further reduce, then you can say that the variance across the components or within a components, if all are equal, if you assume that the variance remains equal across all the components, then we have only one value is sufficient. So, therefore, the number of parameters will be reduced to d plus 1, where d is nothing but the components of the mean vector, right, and 1 is nothing but the variance, 1 is nothing but one variance. So, in this case, instead of hyper ellipsoids, it becomes hypersphere, because all the directions the spread remains same. So, therefore, instead of ellipse, the ellipse becomes a sphere and all. So, therefore, in case of d dimensional, all the eigenvectors, all of them are orthogonal to each other, and all of them have the same eigenvalue and all. So, therefore, you can see that it appears like a hypersphere instead of hyper ellipsoids and all, right. So, that way you can able to represent the Gaussian distribution with the appropriate parameters. And in the next class, we will try to discuss about how do we estimate these parameters, as we have already seen that there are two methods. One is the maximum likelihood estimation method, other one is the Bayesian inference and all. So, we will discuss about those two methods in next class. So, we will stop here. Okay, thank you.